हाँ कर लो, थोड़ा तो टाइम बढ़ के आया है। अच्छा अच्छा पहले से good morning to all of you. So maybe for 2-3 minutes, if you want to ask some questions, doubts, you can ask. Meantime, other students would join. So are there any questions, doubts? No doubts, no questions. Huh? That means you are not actually studying. Otherwise, there would always be some doubts and questions. Okay, so then let me start. So actually, as far as the elements are concerned, particularly solid mechanics, of course, same way you can extend to others. So I am going to do one example on three-dimensional solid mechanics problem, that is element formulation, and then lastly plate bending element. Afterwards, dynamic problems and the numerical integration of dynamic equations of motion, solution of simultaneous equations, and the last topic would be convergence study. So this is what I am going to do. So let me then start. I know the next topic is 3D solid mechanics problem. So in this I am actually going to discuss say essentially brick element, and then tetrahedral element can actually be derived from that by collapsing certain nodes. So what we are talking of, I mean specific case as the, let us say, 8 noded isoparametric. Typically it is actually it's a parallelopiped, so typically it is referred to as brick element. So let me use the same terminology. So 8 noded isoparametric brick element, that is the first example I am going to take. So see here what we are saying, we have certain assumptions. We said no 1D problem, one dimension is significant, other two dimensions are smaller, and the variables are only unknown function of only one coordinate. So then you model those problems as 1D problems. If you have two dimensions which are significant and whatever unknown variables are there, for example displacements and temperature, if they vary in an unknown fashion in two directions, for example temperature in a heat conduction problem in a two-dimensional domain, or plane stress, plane strain, axisymmetric. So all these problems actually fall under two-dimensional problems, and if all the dimensions are comparable and the variables also vary in an unknown fashion, we cannot a priori make some approximation in approximation of the unknown variables in any direction, then the problem is a three-dimensional problem. So if those approximations are not valid, whatever we didn't know 1D and 2D, then we go for three-dimensional problems. So here say let me consider let us say that we have an element in the physical coordinate space, and then know the mapping of this element into the natural coordinate space. So let us say that this is the element we are talking about, and also let me consider a coordinate system. So a coordinate system can have origin in any direction, and in fact the the orientation of the coordinate axis with respect to edges of the element can also be different. So let us say that this is your x direction, and this is y direction, and this is z directions. The nodes are, let me start from the bottom side. So let us say that this is the local node number 1, 2, 3, then this is 4, and then the top side, say this is 5, this is 6, this is 7, this is 8, although it's not necessary that one has to follow this sequence. And you can always deduce tetrahedra from this by, say, if you collapse the top all the 4 nodes into 1, 5, 6, 7 and 8, and maybe say any 2 nodes on the bottom face, that is 1 or 4 or 3 or 4, you get a tetrahedra. So this is the element in the physical coordinate space, and then we map this to the natural coordinate space. So here, as I said, these angles in general can be anything. Of course, ideally this would be 90 degrees as we have studied earlier, and the edges also, this aspect ratio, that is length of this edge to this or any other edge. Theoretically it can be anything, but ideally again from the conditioning of the Jacobian matrix, this would be actually ratio should be unity. But there are limitations, as I said. You can deviate from 90 degrees, so within, as long as the included angle here is between 45 and 135, it's fine, and aspect ratio of any of these edge length ratios, if it is up to 10, it's fine. But if it is beyond that, then of course it has convergence problems. So this is the element in the physical coordinate space. Of course, in the natural coordinate space, this is always going to be cuboid of side 2. So this is the, and it is always going to be cuboid, whereas here it can be any parallelopiped. So I think this should be a little bit here. And here we want to have the coordinate system, which is having origin at the center of this. So let me say that this coordinate direction is high, and this is going somewhere up to the centroid. And then another coordinate axis here, let us say eta, and then the last coordinate axis is, let us say this is, so this is high, this is eta, and this I am using zeta. The origin is at the center. You can use other notations, say for example some of the textbook use R, S and T in place of xi, eta and zeta. I am continuing to use this same whatever we use in the 2D problems. So say this again similar to this is the node number 1, node number 2, 3. You can actually have any sequence, it's actually not necessary, 1, 2, 3, 4, and then from here 5, 6, 7 and 8. So this will be the element, and if you look at the coordinates of node 1 are going to be -1. So if you look at here, of course the coordinates are like x1, y1, z1. For example, if you look at here, so x1, y1, z1, the coordinates here would be x2, y2, z2 and so on. The coordinates here will be, say if we look at node 1, the coordinates are going to be -1, -1, -1. If you look at 2, the coordinates would be +1, -1 and -1 and so on. Same you can write the coordinates once you understand the origin of the coordinate axes and their orientation. So similarly node 3 would be 1, 1 and -1. 4 would be the coordinates of node 4 are going to be then -1, +1 and -1. Like that, you can look at the coordinates of all other nodes. So this is the element in the natural coordinate space. This is the element in the physical coordinate space. And I already mentioned to you that this can be deduced to a tetrahedra by appropriately collapsing the nodes. If we collapse make all the 5, 6, 7 and 8 as one node, and similarly say any one these 1 or 4 or 3 and 4. So base will be a triangle, and then one point on the top and joined to the vertices of the base triangle, you get a tetrahedra with 4 faces. So it can be deduced from this. So now what we want to look at in this, say as a solid mechanics problem, so if you look at the displacements, so what we are saying here, since this is a 3D problem, we will have 3 displacement components which are unknown functions of x, y and z, all the 3 independent coordinates. So 3 displacements which are unknown functions of x, y and z. So u is the displacement along x direction. So displacement here is u, displacement along this direction is v, and the displacement in this direction is w, and they are functions of x, y and z for static equilibrium problems. And so also the strains. Strains again, if you want to write in terms of the separately, and then of course you can always put into the vector notation. So like epsilon x is del u by del x, rate of change of u along x direction, epsilon y is, of course we are assuming that the displacement gradients are small, so here the nonlinear terms in the expressions for strains are actually negligible. So this is del v by del y, and epsilon zz is del w by. So this is standard relations you do in solid mechanics. Gamma x y is del u by del y plus del v by del x, and gamma y z is del v by del z plus del w by del y, and gamma x z is del u by del z plus del w by del x. So these are your strains, and you can put them in the vector form like what we have been doing so far. So you can put into all of these into a vector form, and then similarly you have now the stresses are going to be related to again 6 components of stresses. So if I write this as a column vector, all the 6 components, sigma yy, sigma zz, tau xy, tau, this is just a some preliminaries. This, and you can denote this as just a let us say vector sigma, and this is equal to constitutive matrix C. You will have a constitutive matrix, and then the strain vector epsilon, and that would be again epsilon xx, epsilon yy, epsilon zz, and then gamma xy, gamma yz, and gamma zx. So if you want, you can also write this as C into vector epsilon. So epsilon is nothing but that is basically this vector. Similarly, sigma is this. So you can say sigma is equal to C into epsilon. So this is your stress strain relation. Now typically for depending on the material, whether the material is linear elastic, isotropic, or orthotropic, the form of C would be different. So for example, for linear elastic isotropic materials, the form of C is now the general like similar to what we did in fact for the axisymmetric case. So the form is similar, E upon 1 plus nu into 1 minus 2 nu, and then of course now isotropic material means only normal stresses and strains are coupled, but no coupling between shear and normal strains and vice versa. So here what you have is 1 minus nu, then 0, 0, 0. That is this multiplied with epsilon vector will give you sigma xx, and then here nu 1 minus nu 0, 0, 0. This is a standard relation, so no, I am not going into the details of this. So then this is 0, then here you should get G. So this is 1 minus 2 nu by 2, 0, 0, and then you have 0, 0, 0, 1 minus 2 nu by 2, 0, and finally 0, 0, 0, 0, 1 minus 2 nu by 2. So this is the constitutive matrix for linear elastic isotropic material in terms of 2 independent material constants, that is Young's modulus E and Poisson's ratio nu. Nu is the Poisson's ratio, is the Young's modulus. So this is as far as the your displacement. So this is now 3 variables here, 6 components of strains, corresponding 6 components of stresses, and then the constitutive relation. Now finally, to develop the element level governing equations, we need to write the expression for total potential energy. Of course, one can also come from the Now you have three stress equations of equilibrium, then write the weak form corresponding to those, and then from the weak form you can actually finally write either your integral functional or develop the element level governing equations. Here I am writing directly the total potential energy functional. So now this is going to be consisting of, say, I, which is the strain energy, half of integration over volume, capital V I am using for volume, and this would be sigma xx into epsilon xx plus sigma yy into epsilon yy and so on. So we can write that as sigma transpose into epsilon. So this would be epsilon dV. So this is your strain energy part, which is actually half of sigma xx into epsilon xx plus sigma yy into epsilon yy plus sigma zz into epsilon zz plus gamma xy into tau xy and so on. And then you will have no body forces, let us say, so that no within this element there are certain body forces having components along x, y and z directions. So the potential of those forces, again with respect to datum as the undeformed configuration, you get the body force contribution as integration again over volume, and then let us say the body forces are Fbx, Fby and Fbz along the x, y and z direction. So I can write the potential of those as integration over Fbx, Fby, Fbz, and then this is dV. So this is actually Fbx into u plus Fby into v plus Fbz into w. So Fbx, Fby, Fbz are the forces per unit volume. So into dV gives you the total force over a differential volume dV, then into u gives you the work done, negative of that gives you potential, and so for the other Fby and Fbz. And in addition, you can have, because this element is in general separated out from the inside of a volume, bigger structure. So you are going to have the tractions and all the phases in general, what we call as the potential of internal forces, and that is going to be in terms of integration over surface, and say again they can have those traction forces on the three sides. On a surface you can have a traction component along x direction, you can have along y direction, you can have along z direction. So the corresponding potential is going to be, let us say those tractions are T and x, T and y and T and z, and into ds. So this is now surface integral, essentially integration over the outer surface of an element. So this is, of course, in addition you can have some concentrated forces also. We are only including these, and you can always include the concentrated forces in this. So this is the form of your total potential energy functional. If we want to develop the element level governing equations from total potential energy functional directly. So now what we want to do is, if you look at the sigma finally is C times epsilon. So as far as the first term is concerned, you can rewrite that as sigma as C into epsilon. Sigma transpose would be epsilon transpose into C transpose, since constitutive matrix is symmetric. So you can write this as epsilon transpose into C into epsilon and then dV, and there are other two terms. So then the other two terms remain same. So the first term can be written like this. Now as far as if you look at the interpolation, epsilon is in terms of first derivatives of the displacements with respect to x, y and z. So what we need is, whatever solution we assume, it should be differentiable at least once with respect to x, y and z. So then what essentially we are doing, so now if you look at the approximation within the elements, so what we are, since the highest order derivatives of the displacements which are unknowns present in the integral functional are first derivative, so whatever we assume must be differentiable at least once. And in terms of, if you look at now the continuity, so the displacements, these three displacements must be continuous across the elements. Here these are the only primary variables, their derivatives are strains, that is in terms of essentially stresses, so say no secondary variables. So we have only primary variables here as these displacements. That means we get a continuous structure if these displacements are continuous after the deformed configuration. So now as far as the approximation is concerned, we would like to assume, say u, and again to satisfy the inter-element continuity requirement for all general parallelopiped in physical coordinate space, we assume this in the natural coordinate space. So we have say a constant term A0 plus A1 xi plus say A2 eta plus A3 zeta. So these are all linear terms, and then the bilinear terms. So say A4 then xi eta plus A5 you can have say xi and xi and zeta and eta and zeta. So you can have xi and zeta plus you can have A6 into eta and zeta, and plus so we have now these combinations, and plus you can have, so one more term we will have is A7, which is xi eta and zeta. So this is a constant term. Obviously any approximation must have a constant term, and we need, obviously, since we are talking of an 8 noded element, and so we have to have 8 constants here, so that they can be represented in terms of 8 degrees of freedom corresponding to u, similarly for v and w. So now 8 means first linear terms in xi eta and zeta, then the products xi into eta, xi into zeta, and then eta into zeta, and then this product xi eta zeta. So this is the kind of polynomial you can assume for each of these variables. So now similar thing you will have for b, same thing for w, and since this is an isoparametric formulation, so also for x, y and z. So say like x is equal to, so here a, b, c, so if you use here d, so d0 plus d1 into xi plus d2 into eta, and so on. This form is going to be similar to what I have written for this u. Then what you do is basically, as we did earlier, that by u is equal to u1 at first node, where xi eta and zeta are -1 -1 -1. So like that you can set up 8 equations, and those 8 equations can be used to express a0, a1, a2, a3 in terms of u1, u2, u3 up to u8, and then the coefficients of u1, u2, u3, u8 would be actually your shape functions. So the way we have these are actually the steps involved. So if you follow all of that, so finally you can write your u as summation over all the 8 nodes, so I going from 1 to 8, ni ui. Similarly you can write for v and w as well, I going from 1 to 8, ni vi, and w is equal to ni wi, I going from 1 to 8, and so also for x, y and z. So you would be able to write x also as I going from 1 to 8, and ni xi in isoparametric formulation. Similarly your y is going to be 1 to 8, ni yi, and z would be similarly I going from 1 to 8, ni zi. Only difference is between these two sets is, in the first set ui, vi, wi, they are unknown degrees of freedom, values of the variables at the node points, whereas xi, yi, zi are the known coordinates of physical coordinates of these nodes. So of course we are through these relations are expressing x, y, z in terms of xi, eta and zeta. So now if you look at when we follow this procedure, what I said here briefly, the expressions for these shape functions, say for example n1 corresponding to first node. So let me again sketch here rather than going up and down again and again. So this is the element in the natural coordinate space, and we had said that this is our node 1, this is node 2, this is 3, this is 4, and this is 5, this is 6, this is 7, this is 8, and the coordinates this is your xi going somewhere up to the centroid, this side is your eta, and from here this is your zeta. So if you want to write the shape function for this node, the shape function should be unity here, and it should be 0 at all the other nodes. So that is remaining nodes 2, 3, 4, 5, 6, 7 and 8. So if you want to write that, for this case you can write the shape function for node 1 as the product of equation of this surface, equation of this surface, and equation of top surface. So what would be the equation of this face? which is 6, 2, 3 and 7. What would be the equation? Xi equal to 1, because no, this is the phase where xi is 1. So you can write that as 1 minus xi, because xi is varying from minus 1 to plus 1. So rather than writing it as xi minus 1, we are writing 1 minus xi, so that it will always be positive. So 1 minus xi is the actually no equation of this surface. Then if you look at the equation of this surface, for this surface eta is 1, so you can write that as 1 minus eta. And then the top surface where this zeta equal to 1, so you can write that equation as 1 minus zeta. And so if you do this, now if you look at, you can cross check that this product is going to be 0 at all these nodes 2, 3, 6, 7, 4, 8 and 5. It would be 0 at all those nodes, because no, the values of xi, eta and zeta, if you put of corresponding to these nodes, you will find that this would be 0 there. Now if you put the coordinates of node 1, coordinates of node 1 are minus 1, minus 1, minus 1. We had, so it's on the opposite side. So when you put minus 1, minus 1, minus 1 here, you will get 2 into 2 into 2, 8. So you divide it by 8, so that n1 is unity at node number 1. So this is the shape function n1 corresponding to first node in terms of natural coordinates xi, eta and zeta. So similarly, if you look at n2, that is now this node, so you will have to make sure that this is 0 at the remaining nodes and unity at this particular node. So you will find that is going to be product of the equation of this surface, equation of this top surface, and the equation of the bottom, the back side surface. So only change is going to be in the equation of the back side, which will replace this 1 minus xi by 1 plus xi. So you will find that this would be 1 plus xi, 1 minus eta, 1 minus zeta. So same way you can write all the other 8 shape functions. So this is 1 by 8. Maybe there is actually standard format you can write this. So we shouldn't be spending more time on this. So similarly n3, now when you go to this, you can also write by observation. Now we are moving, when we go from 2 to 3, we are moving in the eta direction. So sign of eta would change in the shape function from 2 to 3. So this would remain same. This would become 1 plus eta and 1 minus zeta. And then when you write n4, so 3 to 4, we are shifting in the this xi direction. So sign of xi would change, which would make it 1 minus xi, 1 plus eta and 1 minus zeta. So similarly, if you look at n5, n5 is basically now you are shifting from, so of course it's again the product of 3 surface equations basically. So when you look at 1, you are moving from 1 to 5 in the zeta direction. So the in the shape function of n1, if you replace zeta by minus zeta, you get actually the shape function. So 1 by 8, 1 minus xi, 1 minus eta, 1 minus zeta. So similarly n6, so this is 1 plus, yeah, this is going to be plus. So the n6, similarly n6 is then going to be, now the sign of xi would change, so this would become 1 plus xi, 1 minus eta and 1 plus zeta. So in all these you find the bottom 1, 2, 3, 4, this term is negative, here it is going to be positive. So n7 is 1 by 8, when you go to node number 7, you are shifting in the eta direction. So 1 plus zeta, 1 plus eta and 1 plus zeta. And so also finally n8 is 1 by 8, and then from 7 to 8 you are shifting in the zeta direction, so which is 1 minus zeta, 1 plus eta and 1 plus zeta. So these are your shape functions, which is if you understand you can write them. So similar to what we did actually for 2D problem. So only thing is now you have 3 coordinates. So once you have these shape functions and this interpolation, whatever interpolation we have here, finally we want to put this in the form of product of matrix and vector. So I can put all the 3 interpolations for u, v, w together in the form of your H matrix, interpolation matrix, and vector of elemental degrees of freedom. Now the arrangement of vector of elemental degrees of freedom is going to be first node, say the displacement along x direction u1, v1, w1. So these are the degrees of freedom of first node. Values of displacements along x, y and z directions, then u2, v2, W2 and so on. Finally, we will have U8, V8 and W8. So this is your vector of elemental degrees of freedom. As you see here, this is going to be 24 by 1. So we have 24 elemental degrees of freedom. And here if you want to put it, so U is like N1 U1 plus N2 U2 plus N3 U3. So here you will get U as N1, then 0 0, N2 0 0. I will not write the entire thing, N3 0 0 and so on. So this will give you N1 into U1 when you multiply, plus N2 into U2 plus N3 into U3, finally N8 into U8. Similarly for V should be N1 V1 plus N2 V2 plus N3 V3. So you have 0 N1 0 0 N2, then 0 0 N3 and then 0 and so on. And for the last one you will have N1, then 0 0 N2, 0 0 N3 and so on. At the end you will have here N8. So this, as usual, you call it as interpolation matrix H, and this has the vector of elemental degrees of freedom DE. And this is your H, as we have said, this is 24 by 1 and this is 3 by 24 H matrix. So obviously you see these are all cannot be done manually. If you want to solve problems, you have to write a code or use a package, and you can then only solve problems, because the sizes of the matrices, multiplications and calculations are too many. So only we can conceptually look at how the formulation is done. So this UVW are expressed in terms of interpolation matrix H and the vector of elemental degrees of freedom DE like this. Then what we need is, in the integral functional you have the strain vector. Now this strain is a tensor, but we have written it in a vector form using all the 6 components. So we are saying that the epsilon, which is all those 6 components, I am not going to repeat all of them again. So epsilon xx, epsilon yy and so on. So this if we want to write similarly. So we want to again write this in terms of derivatives of the shape function and your vector of elemental degrees of freedom. So it's here U1, V1, W1 and so on, and finally you have U8, V8 and W8. So see, epsilon xx is del u by del x. Again, the best way to evaluate the strain displacement matrix, that is the matrix which is coming here, is first work out the derivatives of the shape functions with respect to x, y, z, and then use them here. You need not introduce separately the derivatives of the shape function here with respect to xi, eta, zeta and Jacobian matrix. You can directly write that in terms of derivatives of the shape functions with respect to x, y, z. So epsilon xx is del u by del x. So I can write that as del n1 by del x into u1, plus the next term would be del n1 by del n2 by del x into u2. So I put here 0 0 because in the multiplication, so that the v1 and w1 do not contribute, and then you will have del n2 by del x 0 0 and then del n3 by del x 0 0 and so on. The last of course would be 0. Then epsilon yy is del v by del y, so that is 0 del n1 by del y 0, and then you have 0 del n2 by del y and then 0 0 del n3 by del y again 0 and so on. See, epsilon zz similarly would be 0 0 del n1 by del z, 0 0 del n2 by del z, and so that when you multiply you will get epsilon zz, which is del w by del z. And here of course, as we see, we are not making any approximation on any of the strains. And then when you look at the fourth one, say gamma xy, which is del u by del y plus del v by del x, so you will have del n1 by del y here and then del n1 by del x. So this will give you del n1 by del y into u1 plus del n1 by del x into v1, so that is coming from del v by del x. So same way this will be then 0 and then del n2 by del y and del n2 by del x and 0 and so on. So like that you can write for the remaining 2 more components of strains in a similar manner. So this is what we call this as strain displacement matrix B and into vector of elemental degrees of freedom. You will find again this is 24 by 1 and now B here is 6 by 24, right. So this is your B is your strain displacement matrix. Now before we substitute this, I also want to look at how we will be evaluating these derivatives. So see, as far as the shape functions are concerned, we have written them in terms of xi eta and zeta. We can find out their derivatives explicitly with respect to xi eta and zeta. For example, del n1 by del xi would be minus 1 by 8 into 1 minus eta into 1 minus zeta, like that. So you can get their derivatives directly with respect to natural coordinates, but then you finally need the derivatives of these with respect to xy, that is xy and z physical coordinates. So again we use the same concept which we actually use for the 2D problems. That is, if we consider a function and again the starting point is an inverse approach. So if you have in general, let us say, some function which is a function of x, y and z, and I want to differentiate this with respect to xi eta and zeta, wherein x, y, z are in turn functions of xi eta and zeta. So I can write this as del f by del xi is equal to, is exactly similar to what we did for 2D. So this would be del f by del x into del x by del xi plus del f by del y and del y by del xi and plus del f by del z and del z by del xi. Why this particular form? Because x, y, z are also interpolated in terms of natural coordinates. So we directly have the explicit expressions for these. So I can write can get del x by del xi, del y by del xi, del z by del xi. Irrespective of what this function f is, it can be n1, n2, n3 or any other function, these are going to remain same. There is no derivatives of x, y and z with respect to xi. So similarly, del f by del eta you can write in exactly in a similar manner, that del f by then del x into del x by del eta. You have to just differentiate between x and eta. So plus del f by del y into del y by del eta plus del f by del z into del z by del eta. So now since there are three coordinates x, y, z in the physical coordinate space, xi eta zeta in the natural coordinate space, so we will have those three, del f by del xi, del f by del eta and del f by del zeta would be similarly del f by del x and del x by del zeta plus similar manner del f by del y by del zeta plus del f by del z into del z by del zeta. So if this the way we had done earlier, in the operator form, if you want to write this, we can take out f, because that these equations are applicable for any function. F can be any function. So you can write this as del f by del xi, del by del eta, del by del zeta. This operator, the derivative operator, is equal to what we have the derivatives of x, y and z we keep inside this matrix, and then the derivatives with respect to x, y here, del by del x, del by del y and del by del z. So here what you have is like this del x by del xi, del y by del xi and del z by del xi. Then you have next del x by del eta, del y by del eta and del z by del eta. Then you have del x by del zeta, del y by del zeta and del z by del zeta. So this is we call it as earlier, this has the Jacobian matrix, and of course then this is the derivative operator, del by del x, del by del y and del by del z. So if we want now actually what we want is, because we have expressed our interpolation functions in terms of natural coordinates, so we want the inverse of this. So I can say that del by del x, del by del y and del by del z, that is these derivative operators would be equal to here j inverse and into then the derivatives with respect to xi eta and zeta, del by del zeta. And as usual, like let us say when you invert this j, you will get again a 3 by 3 matrix, and let me call that as like your j11 star, j12 star, j13 star. This is nothing but elements of j inverse, and this is j21 star, j22 star and j23 star. This would be, in general this would be actually unsymmetric, in specific cases it can be symmetric, j31 star, j32 star and j33 star into of course this del by del xi, del by del eta and del by del zeta. So what it means is, now the the left hand side you have basically the same thing here, And so if you want to write explicitly for each of these, so you can say del by del x is j11 star into del by del xi plus j12 star, that first row you are taking, no, the first row from here, so you are taking first row from this multiplication also. So the first row into this, what will give you j11 star del by del xi, j12 star into del by del eta plus j13 star into del by del zeta. So like that, now you want to write del by del y also in a similar manner, which would be j21 star del by del xi and so on. Now you can write no this no row into this column again, and similarly del by del z would be j31 star into del by del xi plus j32 star into del by del eta plus j33 star into del by del zeta. So once we have defined our Jacobian matrix and the inverse of the Jacobian matrix, if we have derivatives with respect to xi, eta and zeta, we can work out the derivatives with respect to x, y and z. That is what these relations are telling you. For example, if no, I want del n1 by del x, which is needed no in the strain displacement matrix B. So del n1 by del x is going to be, here I put n1. I operate del by del x on n1. So on the right hand side I will have these three terms. So which is j11 star into del n1 by del xi plus j12 star into del n1 by del eta plus j13 star into del n1 by del zeta. So like that, no, you can write, say if you want del n1 by del y is equal to j21 star. Now you want this, so j21 star into del n1 by del xi plus j22 star into del n1 by del eta and plus j23 star into del n1 by del zeta. Like that you can write the all the derivatives of each shape function. Now you can have n1 into n3. So this is how you will actually evaluate these derivatives of the shape functions with respect to x, y and z, which are needed here in the strain displacement matrix, that is this matrix. Once you evaluate this, now you are ready to substitute this in your integral, functional and all of the element level governing equation. So again, if you come back to I, which was half integration over volume, and this was epsilon transpose C into epsilon. Epsilon transpose can be written as epsilon is B into DE. So we will have here DE transpose into B transpose, because epsilon is B into DE, its transpose is this. Then in between you have a constitutive matrix, and then again epsilon, which is B into DE, and then the integration over volume dV. And of course the other terms are then body force term, which is integration again over volume, UVW in transpose into FBX, FBY, FBZ, and that is H into DE, so it becomes DE transpose into H transpose, and then of course you have body force vector FBX, FBY and FBZ dV. And the last term was the surface integral, which is minus integration over surface. Again it was UVW transpose, so that would be D transpose into H transpose, and then the TNX, TNY and TNZ ds. So this becomes your, this is again standard actually, no, same way the way we did earlier. And now this, as since everything here is expressed in terms of xi and eta, so we can now write this integral dV in terms of natural coordinates. So what I can actually do is write this, and since this d is independent of xi, eta and zeta, I can take this out of the integration, similarly that side. So I can write this as half and then this as d transpose, then triple integral -1 to +1, because all the natural coordinates are going from -1 to +1, and then here you have b transpose into c into b, and this I am going to take the other side. So dv can be written as determinant of j into now d xi, d eta and d zeta. So this is the first term, and of course so this is finally, if you look at, is going to be, this is what is your stiffness matrix, and this side you will have DE. So if you look at DE is 24 by 1, we have seen its transpose is 1 by 24. Here if you look at B is 6 by 24, this is 6 by 6, B transpose is 24 by 6. So finally you will see here 24. So finally you see the center matrix in between what we have is actually going to be 24 by 24 matrix. So now the element level stiffness matrix for 8 noded brick element is 24 by 24. That is what you get, and the vector of elemental degrees of freedom we already talked about. So this is the first term, and the volume integral, as I said, now we are writing in terms of the natural coordinates. So the way we have for 2D, similarly for 3D, now we have the dV in the physical coordinate space equal to determinant j times basically the differential volume in the natural coordinate space d high d eta and d zeta. So that, then similarly now in this you can take out your d transpose common, then you have h transpose fbx, fby, fbz, dv equal to, and the last term. So the other two terms are basically in a similar manner. Now again see here what we say, because when we develop the element level governing equation, so for equilibrium again this delta for arbitrary delta dE, this delta I, that is variation in the integral functional, should be equal to 0. So now for equilibrium, delta I should be equal to 0. For arbitrary means it is not fixed, no, we can vary arbitrary delta dE. This delta symbol is for variation. So from this you get now the way we did, now see this is same as we whatever we do in 1D problem, the same thing is also here in 2D as well as in 3D. So you have the first term D transpose this side, D this side, when you take its variation, so variation of this into the whole thing plus this side entire thing into variation of the second term. Since the whole thing is a scalar, you can write one term like the other, so this half will go. So finally this delta of I can be written as, say, delta of dE transpose, and what you will have here is, now let me call this entire thing as KE, that is element level stiffness matrix, so I can call that as KE. Then this dE would be there here, so this dE left out, and similarly now this delta D transpose is actually taken inside. So let me call this quantity H transpose FBX, FBY, FBZ as F external. So F external for the element, and let me call that as F internal. So as we were doing earlier, this is actually equal to 0. That is what we are saying, delta I equal to 0 for arbitrary delta dE, and this implies, since this is arbitrary, so if this whole product has to be 0, that means this must be equal to a null vector. So this gives you the element level equation, which is KE into dE, and you can take the other terms to the right hand side, so you can write it like this. So F internal for the element, and various quantities here are KE is integration -1 to +1, -1 to +1, and then this is B transpose, and then again C into B, determinant of J into d high d eta d zeta. Your F external for the element is again this triple integral -1 to +1, -1 to +1, and then you have H transpose, essentially this term, this is the term which I refer to as F external. So H transpose into body force FBX, FBY, FBZ, and then you have this again can be written as determinant of J into d high d eta and d zeta. And F internal for the element is again in a similar manner -1 to, this I will leave as it is, not minus, because the surface integral. So depending on the surface you will have to actually evaluate, so I will just leave it as a surface integral. It is H transpose and then Tnx, Tny and Tnz ds. This has to be evaluated of course properly. So see, the form of the element level governing equation is actually same, only thing is now your stiffness matrix is 24 by 24, this vector is 24 by 1, and this is 24 by 1, this is also 24 by 1. Now if you change this to from 8 noded, you will again find that the strains are basically going to be, if it's a element is a, let's say, cuboid in the natural physical coordinate space, then the strains within the element are going to be actually constant. Say for example epsilon xx would be constant along x direction and so on. So you want to improve the performance of the element, you can go for 20 noded element. So then you can have nodes at the center or the faces as well. Then next is of course 27 noded. So similarly, you can improve upon this. Now finally, if you look at the evaluation of this integral, this integral again, these integrals are evaluated numerically. Gauss quadrature numerical integration. So for the integration, if you look at the KE, like we did for the 2D problems, so this is written as summation over, now say I equal to 1 to n, j equal to 1 to n, and k equal to, let us say, 1 to n, where n is the number of Gauss points, and then this B transpose into C into B into determinant of j. This whole thing is evaluated at, say, xi I, eta j and zeta k into wi, wj, wk. So these integrals are again evaluated numerically. Again, you don't do the explicit integration. Explicit integration means then you have to multiply all of these and then do the individual integrations. So we don't do that. Now this is a triple integral, so we will have of course triple summation. So for this case, if ideally no element is a cuboid in the physical coordinate space, then 2 points in each direction would be sufficient. So 2 into 2 into 2 actually will have 8 points. So that means this entire product you will be evaluating at 8 points and then summing it up. That will give you the finally element level stiffness matrix. So this is how you do the formulation for a 3D element, and as I said, this can be collapsed to a quadrilateral element. So by the tetrahedral element. So if you collapse the top nodes into one, and similarly one of the to any two bottom nodes, you get a tetrahedral from this. And of course one can always do the separate formulation for that. So I think I want to stop here. Maybe I also wanted to distribute the minor answer sheets, and we will continue tomorrow. That is, I mean, to cover at least all aspects of elements in solid mechanics. I also want to briefly discuss about plate bending elements and then move on to the other topics. So tomorrow maybe I will discuss plate bending element and then continue further. And if you have any questions and doubts, you can ask after the marks. These answer sheets are distributed.